This video's topic is higher derivatives, higher order derivative. So just like the way we can find the first derivative, the same way we can find the second derivative, third derivative, fourth derivative, and so on. So first derivative is represented by y prime, second derivative with y double prime, first derivative f of f prime of x, f double prime of x, third derivative y triple prime or f third derivative of x. Fourth derivative is written with the parentheses on the top instead of the Roman letter 4, and the nth derivative is also written with the parentheses on the top. So dy dx or d dx of f of x, d square y dx squared, d square f of x over dx squared, and so on. So these are the notations for higher derivatives. And this is the notation for nth derivative. Sometimes you're looking for the nth derivative, and by looking at a pattern, you can evaluate the nth derivative easily and quickly. So here's an example. Y is equal to x to the fourth plus x cubed minus 2x squared plus 1. Another interesting thing to note is polynomials. Eventually, their derivative becomes 0 because polynomials are always smooth, continuous curves. So whatever is the degree of polynomial, that's how many derivatives will exist. Beyond that, so if it's a fourth degree polynomial, the fifth derivative will be 0 for this polynomial. Let's take a look. Y prime would be 4x to the third plus 3x squared minus 4x. 2 times 2 would be minus 4x, and derivative of 1 is 0. Y double prime is 12x squared plus 6x minus 4. Y triple prime is 24x plus 6. And the fourth derivative would be equal to 24. And if I go ahead and find the fifth derivative, that's going to be 0. So whatever is the degree of polynomial, that's how many derivatives will occur. Beyond that degree, beyond that point, all the derivatives will be 0. So if I ask you to find the thousandth derivative here, that is going to be 0 for this function. And for rational functions, their derivatives are never going to be 0. So for rational functions, the derivative is never going to be 0, but for polynomials, only as many derivatives will occur as the degree of polynomial. Beyond that, the derivatives will not occur. Let's check out f of x is x to the third power. And if I want to find the third derivative, first derivative would be 3x squared, second derivative would be 6x, and the third derivative is 6. What's going to be the fourth derivative? That's going to be 0. Every derivative beyond the fourth derivative is also going to be 0. Next, we are looking for a fourth derivative here. dy dx is given, so d square y dx squared will be 20x to the third minus 3. D to the third power dy cubed would be 60x squared, and the fourth derivative would be equal to 120x. Fourth derivative, let's check. So it's the fourth degree polynomial. The first derivative is given. Okay, so we're given the first derivative and we follow. We were not given the function y. We were given the first derivative. Eventually, we'll also talk about if you're given the dy dx, how can you tell what is the function whose derivative is given. So we found the second derivative, third derivative, and the fourth derivative. And it's originally, this would be a fifth degree polynomial, because we were given the first derivative. And when we take the derivative, we reduce the exponent by 1. So if it was a fifth degree polynomial, the 5 derivatives will occur, and beyond that, other derivatives will not occur. Acceleration and velocity. Acceleration, velocity is the rate of change. So first derivative is the velocity, because that's what rate of change is. First derivative is velocity at a point or in general, and acceleration is the derivative of velocity. So acceleration will be the first derivative is velocity, which is derivative of position function. Derivative of position with respect to time. Derivative of position with respect to time. And acceleration is derivative of velocity, and that is the second derivative of position. So second derivative of position is acceleration, which is derivative of velocity. Okay, the position of a particle is given by this equation. Find the acceleration of the particle when t is 3. Okay, so the t is time, x is the position. So we want to find out the acceleration here. First, we want to find dv dt. That's going to be derivative. This is not going to be dv dt, but the velocity is equal to dx dt, because the position is labeled using the variable x. So dx dt would be equal to the derivative of this function with respect to time. So that's going to be 12t squared minus 6t plus 5. Now we were looking at the second derivative, d squared x dt squared, which is acceleration. Acceleration is going to be 24t minus 6. Now we wanted to evaluate the acceleration at a special point when t is equal to 3. So that's going to be 24 times 3 minus 6. And 24 times 3 minus 6 would be 72 minus 6, which is 66. And there's no unit, so I'm just going to leave it as 66 units. What can be the possible units of acceleration? They can be meters per second square. So unit of the distance divided by unit of time squared, because originally our distance is usually given in meters or kilometers or miles. Okay, find the fourth derivative of this function. First of all, take a look. It's not a polynomial, it's a rational function, because you have x to the power. It's a radical function. It's a mix of radical and polynomial. So the derivative is not going to be 0 for this function. It's never going to be 0. Let's go ahead and find the first derivative. That would be 18x to the fifth plus 2 plus 4 times 1/2 x to the power half minus 1 would be negative 1/2. Second derivative, 18 times 5 is 90x to the fourth. Derivative of 2 would be 0. And that's a 2 plus 2 times negative 1/2 x to the power negative 1/2 minus 1 is negative 3/2. Third derivative is going to be 90 times 4 is 360x to the third, 360x to the third plus 3/2, because this is going to be gone and it's going to become positive, 3/2 x to the power negative 5 over 2. And now we are ready for the fourth derivative. That's what we were looking for. 360 times 3 is 1080x squared minus 15 over 4. 3 times 5 is 15. 2 times 2 is 4. X to the power negative 5/2 minus 1 would be negative 7/2. And that's going to be the fourth derivative. That's all we were looking for. Another example, find the third derivative at x equals negative 1. So I'm going to first find the general derivative, first derivative and second and third. Then I'm going to plug x as negative 1 in there. F prime of x turns out to be 3x to the, it would be 15x to the fourth minus 4x minus 14x to the power negative 3. The second derivative would be 60x to the third minus 4 plus 14 times 3 is 42x to the power negative 4. The third derivative would be 180x squared, and the derivative of 4 is going to be 0. 42 times 4 is 168, 168x to the power negative 5. All right, so we wanted to evaluate this derivative at negative 1. So I'm going to replace every single x by negative 1 and see what does that give me. Okay, this was an 8. Negative 1 squared, it wasn't 1, yeah, it is 180, minus 168 times 1 over negative 1 to the fifth power would be negative 1. So that turns out to be 180 plus 168, which is 180 plus 168, 348. And that's going to be our rate of change at the point negative 1 for this given function. That's the slope of the tangent line. And that's also the limit at that point. Okay, polynomials have a special property like we mentioned earlier. Eventually their derivatives become 0. So if a polynomial has a degree n, then we'll have the first n derivatives. But beyond that, all the derivatives will become 0. Rational functions never have the derivative that becomes 0. So now we're going to practice finding the nth derivative. So how do we find the nth derivative? Let's see. First of all, I will have to find first few derivatives, look for the pattern, and then come up with a rule for the nth derivative. So y prime would be negative 1 x to the power negative 2. Y double prime is negative 1 times negative 2 x to the power negative 3. Y triple prime is double prime, triple prime, negative 1 times negative 2 times negative 3 x to the power negative 4. And now I'm going to find the fourth derivative. You don't have to find too many. Usually, once you see 5 derivatives, you start seeing the pattern. In some cases, it's really difficult. It's time consuming to figure out the nth derivative. This one is fairly simple. So I can say the nth derivative, y and x, is going to be, I can see the pattern. The first term is negative. The second one is going to be positive because negative times negative will multiply. The third one is negative. Fourth one will be positive because I have 4 negatives multiplying. And in the first term, I have the coefficient 1. In the second term, coefficient 2. Third term, 1 times 2 times 3. Fourth term, 1 times 2 times 3 times 4. So I have n factorial as my coefficient. Actually, let's take care of the positive and negative first. Okay, so negative 1 to what exponent? Negative 1 to the nth power. When I'm doing the first derivative, this will give me negative. If I'm doing the second derivative, negative 1 to the second power will become positive. Then we have n factorial x to the power. Look at this pattern here. For the first derivative, this is 2, second derivative 3, third derivative 4, fourth derivative I have a 5. So one next number, and it's also negative. So it's going to be negative n plus 1. And that is my nth derivative. Using this formula, you can find the 20,000th derivative for this function, and they're going to be never 0 because it's not a polynomial function. It's a rational function. Okay, next we're going to look at x times e to the power x, and we're going to find the nth derivative for this function as well, x times e to the power x. And this is also not a polynomial function because polynomials have integers as the exponents for the variable. Okay, so again, let's go ahead and look at first few derivatives. Y prime would be first function times derivative of second plus second times derivative of first, which is x e to the power x plus e to the power x. And if I get e to the power x out, x plus 1. Second derivative would be derivative of this function. And this piece is going to keep on yielding the whole thing again. So x e to the power x plus e to the power x plus e to the power x turns out to be x e to the power x plus 2e to the power x, which is e to the power x, x plus 2. Third derivative, again, if you look carefully, you don't have to do a whole lot of work over and over because this piece is the only one that will yield the same baby again, x e to the power x plus e to the power x plus 2e to the power x turns out to be x e to the power x plus 3e to the power x, which is e to the power x times x plus 3. Now one more, we'll do the fourth derivative. I'm going to give myself a little more room here. I don't want them to be too close. Fourth derivative. So for the fourth derivative, we would have x e to the power x plus e to the power x plus 3e to the power x, which is x e to the power x plus 4e to the power x, e to the power x times x plus 4. And this one is not too complicated to find the pattern here. So y and x, the nth derivative, is going to be, I can see they all have e to the power x. So I'm looking for a pattern in these derivatives. They all have e to the power x, and they all have x plus some number, and that number is same as whatever derivative you're doing. If you're doing second derivative, then you have x plus 2, third derivative x plus 3, fourth derivative x plus 4. So this is going to be x plus n. That's an n, x plus n. And that's it. That's the nth derivative here. Okay, for most cases, calculating the general formula for n derivative is not always easy. I'll do another video with some complicated calculation of nth derivative. Second derivative and the graph of function. The first derivative gives us the rate of change of original function. First derivative tells us at what rate is the original function increasing or decreasing, and the second derivative tells us the rate of change of the derivative function. At what rate is the derivative increasing or decreasing? First derivative tells us if the original function is increasing or decreasing. Second derivative tells us about the concavity. And we'll talk about more when we do curve sketching. Concavity will be discussed in the curve sketching section.